Uh, Thank you, Graham. Thank you for thank you for introducing me, and I'm so excited to present my talk. I will be discussing my journey with synthetic chemistry and how I have been investigating the doublet-state photophysics of the organic luminescent radical BAxPA. Okay. So I have been studying luminescent compounds and molecules that can absorb and emit light. These compounds are very useful and quite useful for us, right? So we love phones, we love TVs, we love computer screens, and we especially love organic light emitting diodes, also known as OLEDs. These applications and devices contain luminescent compounds that are the reason that we can absorb the content that we seek. And these luminescent compounds are in an emissive layer in the OLEDs. So the OLEDs themselves, or these devices, are inefficient as of now. Because there are several internal quantum inefficiencies involved with the luminescence and emission of these compounds, we have been trying to circumvent this inefficiency by seeking out radicals that luminesce. There are few radicals that actually do luminesce, but before I discuss luminescent radicals, I want to show you guys what a radical even is. So we have two atoms here that are bonded together with shared electrons. These electrons can be broken apart by an excitation with a laser or a strong enough oxidizing reagent. And once they have been broken apart, each atom possesses an unpaired electron. Every atom has an octet rule, which is they want to be paired. All of the electrons have 8 electrons that want to be paired. But because these are unpaired electrons, they are very reactive and highly unstable. So why would we turn towards radicals if they are inefficient? Radicals possess this intrinsic property called the doublet state. Due to the electronic spin of the electron, there are only 2 possible orientations. And we want to take advantage of these highly efficient molecules in hopes of creating a luminescent radical. So there are several types of photoluminescence. And the first type is the most regular general kind. This sad kid in the ground state, probably because he's grounded, has a neutral, no charge, nothing going on with him. He represents an electron, and this electron is in the ground state, neutral, just nothing going on. When this kid is given candy or an intake of energy is given into this electron, this kid will absorb the candy, absorb the energy, and go from the ground doublet state of the radical all the way to a happy kid. Super excited, lots of energy, candy equals energy here. So once we get rid of this candy, take it down, this kid goes back down to the ground state, it's gonna be sad, and it no longer has any energy back at the ground state. But it does emit candy, and that candy is equal to light. And all of that candy is for us to use. And we would like to make a compound, a molecule that gives us all of the candy, all of the light, and apply them into these OLEDs. So that was photoluminescence, and this is now electroluminescence. And when I say that I want to put a luminescent radical into a OLED, I want to place it in the emissive layer, and this is an OLED, an organic light emitting diode. It is made up of several layers: the substrate, anode, conductive layer, emissive layer, and cathode. This substrate is made up of the glass that holds it together. The anode and the cathode both are where the power source are going to be attached. And once we have an excitation, we have this voltage has been applied through the OLED. Once the OLED has gotten that voltage, electrons from the anode to the cathode will move. And while doing so, the cathode will have an excess charge of negative, that will be negative, and then the anode will have a excess positive charge. Once the electrons have been moving up, there are holes that are created. These holes are just the absence of an electron in these conductive or emissive layers. The absence of these layers, the absence of the electron will pair up with the electron in a process called recombination. And in the recombination process, photons will be emitted. So I would like to one day have a luminescent radical that is in an emissive layer that can be introduced into into the layer of an OLED. And that's what we have been working towards. Right. The radicals that we have been studying are very generally the same shape. In 1905, Moses Gomberg produced his seminal triphenyl methyl radical. This radical was super inefficient, super unstable, highly reactive. In the 70s and 80s, further progress has been made in the advancement of radicals, known as the PTM and TTM series, respectively. The PTM radical, the difference is now that there are several chlorine atoms attached to the phenyl groups. These chlorine atoms were attached in hopes of stabilizing this small little unpaired electron in this carbon atom. This carbon atom is very reactive, and in hopes of stopping dimerization from happening or from further reactivity, the chlorines are shielding and protecting the electron from doing so. The TTM radical was also made with just ortho and a para chlorine here, ortho, so right next to this connecting carbon, and the para chlorine, with hopes of also creating a stable radical. PTM does not luminesce, but TTM does. And I will just, so carbazole, it wasn't until 2006 when the Julia group created carbazole BTM, which means that they added a carbazole group, this nitrogen moiety here, into the TTM skeleton, and they saw luminescence, and it luminesced red, and it's very pretty. Very recently, the Nishihara group has created PYBTM and BIS PYTM, where there are just two pyridine rings attached versus just the one. And these compounds both luminesce. They're very beautiful. And I would like to make a luminescent compound with beautiful colors such as this. So I studied their structure, and I'm like, okay, that's cool. That's a nice radical, but it is still very unstable. We turn towards, in our aim to find a stable luminescent radical, we turned towards Kolsch's stable organic radical BDPA. BDPA is far stabler than the TTM or PTM series radicals because of there's a couple of new differences here. Instead of just simple phenyl groups around the triaryl carbon here, we have fluorine groups. Fluorine groups are very, very big and bulky. And they can, and this electron can now resonate between the fluorine groups. This heightened stability and plus the bulky protectiveness of the fluorine groups further stabilize our molecule because this radical can no longer dimerize, nor can it react with other species. I saw that this BDPA molecule was good, but it doesn't luminesce. This is a non-luminescent organic stable radical. We want to make a luminescent radical, therefore we searched the chromophore literature and found 1-azanthone was a very viable option. 1-azanthone has been known to fluoresce as a kettle radical. And this is a picture of it. It's a very beautiful compound that we have to make. So in hopes of creating a luminescent radical, our aim was to introduce this azanthone group into the BDPA radical framework. And that's what we did here. We have BDPA, we have azanthone. Azanthone can fluoresce, BDPA cannot. And we would like to include it in here via a Horner-Wadsworth-Emmons reaction. And created a compound that will be called BAxPA. So I first had to synthesize this azanthone chromophore because it's very expensive. And this is just one of the reactions that I conducted. I have chloronicotinic acid on the left. I have phenol. I reacted it, and I got a very good yield for it after purification, making compound 1. I then took compound 1, treated it with polyphosphoric acid for 20 hours at very, very high heats of 120 degrees. kept it under an anaerobic environment, so under argon and nitrogen, to produce 1-azoxanthone. Once 1-azoxanthone had been confirmed to be produced, right? We confirmed it via NMR and GCMS spectroscopy. We took this commercially available reagent called DCBP. This is a Putovic synthon. Putovic synthons have phosphorus atoms in them. And this Putovic synthon was screened. We screened this reaction with several different bases and found 0% yield. And got none of this Horner-Wadsworth-Emmons product. So there are a couple of problems preventing the ylid formation. A Horner-Wadsworth-Emmons formation reaction creates this beautiful four-member ring molecule. And because this is a very sterically hindered molecule here, all of these hydrogens are repelling this azoxanthone molecule. There's not enough space for this reaction to occur, and I didn't see any quantitative yields of the product. I wasn't even able to isolate the ylid formation either, or any transitions, intermediates. So we turned towards the literature and found that there was a group, Swager's group, who has conducted several Putovic and Horner-Wadsworth-Emmons reactions using fluorinone that gave successful yields of their radicals. I treated benzaldehyde with diethyl phosphate and butyllithium under nitrogen, got very good yields after purification, and got compound 3. Compound 3 was then treated with thionyl chloride, the worst ever reagent in the world. Gave very good yields as well after a 14-hour reaction to give me compound 4. Compound 4 is the Putovic synthon of interest that did give me some yields. Compound 5 was treated with azoxanthone, chromophore, and then we got compound 6. Compound 6 was then treated with 2,7-dibromofluorine, treated with base NDMA at 0 degrees Celsius because this reaction was pretty volatile. And I got the anion, so compound 7. From the anion compound, I treated with silver triplet and NDMA. I stirred it for 10 minutes, and I got the BAxPA radical. It turned from a very beautiful purple inky color to this horrible yellow, pale yellow. And I took a spectra of it, and I got which means that there was a radical in presence, that I have successfully created a radical named BAxPA. However, once I compared it to the BDPA spectra, I saw that there were a couple of differences. One being that the intensity was far reduced, but also that the spectrum had broadened for the BAxPA radical compared to BDPA. So there are several possibilities, and the best, probably most correct and accurate one is that there was just too much oxygen inside of the test tube sample for us to get broadening. However, so a bunch of different routes had failed. They had not worked, or they had not given me enough quantitative yields to be able to quantify the fluorescence, quantify any lifetime. So we searched and scoured the literature, and by the time that it was maybe December, we had found this vinyl phosphonate here. And this vinyl phosphonate is much different from this DCPB because it is less sterically hindered. This is a pin back mechanism that I think will be able to, where azoxanthone will be able to attack and form this ylid. So this is the synthetic pathway that might just work. And here we see that this vinyl phosphonate is pinned back, giving space to the azoxanthone molecule to be able to react with it and form this ylid in the Horner-Wadsworth-Emmons reaction that I hope to see one day. So I did try to make this and use this new synthetic pathway, but I didn't have enough time to finish it. But I did get these couple of reactions with the full arrows versus the dashed arrows. So I treated neopentyl glycols with PCl3, got compound 9, I treated that with ethanol and a 4-hour reflux and got compound 10. I treated compound 10 with benzaldehyde, reacted it with triethylamine and toluene for 2 hours to get compound 11, which was a white residue after purification. I stopped here, and I am hoping that once this project is picked up and some lucky individual takes it on and goes far away with it, they will be able to get BAxPA or compound 8. So the future direction of this project. If we are successful in synthesizing a luminescent radical, then maybe one day this radical can be placed in some emissive layer in any OLED application device. And that's where I hope to see BAxPA continue. Thank you, Graham, for inviting me to and letting me work on your project for all this time. I had a ton of fun. Thank you to the chemistry staff and faculty. Special shout out to DMART for helping me get all of my chemicals and keeping us all safe. And thank you to all of my family, friends, classmates, or anybody who has ever inspired or helped me become a better researcher/scientist. Thank you.
Thank you, Kelly.
Hey, Kelly! Yes, Kelly! Yay!
Woo,
that's my girl.
So with that, I would love to open the floor up for questions. Does anyone have questions for Kelly? I've got one to start the questions off. What is so bad about thionyl chloride?
Thionyl chloride can kill you if you breathe it in. So if you have more than like maybe, I don't even know the amount, maybe I forgot the amount, but I just know that if I take a whiff of it, it will give me a headache. If I take 2 whiffs of it, I'm gonna have to go to a hospital. So thionyl chloride, not good.
I agree. It's terrible. I hate it too. So this is amazing synthetic work. This is fantastic. I wanted to ask questions. I noticed in your last synthetic slide, you had triethylamine as a base to deprotonate that pH. Before, I think you were using butyllithium. Is that right?
Yes, I was.
Yeah. So why is there an actual like acidity difference there, or did you just find that triethylamine actually works better?
So this in the paper that I found from Kumaraswamy, he used triethylamine, and I actually never used triethylamine before until this reaction, and it still gave me quantitative yields of this product. So yes, it did work.
Yeah, cool. Do you think it'd make a difference if like you could even think about pinning that thing back even more, or would that be too hard?
I would love to get rid of that double bonded
like
oxygen.
A smaller ring, right? Yeah.
Oh yeah, a 4-membered ring as well.
Yeah.
Okay, yes, I see. Maybe getting rid of one of the neopentyl vinyl looking ethyls there. That'd be good.
Very cool.
Devin, what do you think about this?
I think it's amazing. I'm super impressed.
Awesome. Okay.
For what it's worth, these graphics are, this is a Kelly original right here, and it's really descriptive picture that's not easy to make on the software. So this is pretty exciting. When she showed it to me the first time, I got very excited to see it because I've been envisioning this in my brain all along, and now it's drawn out. So that's good stuff.
I have a question for you, Kelly. What was your most frustrating and most exciting moment over the past 2 years?
The most frustrating moment, let's see. I think EPR is very frustrating. But honestly, I think it was the screening of all of the bases that frustrated me because sodium hydride, potassium hydroxide, turbotoxide, nothing worked. And I was like, why is nothing happening? I did see the anion form of this compound here. I did see a lot because of the color change. And then when I took an NMR spectra of it, I think we had a missing hydrogen there, a missing proton. But I think honestly, this was probably the worst reaction because it was just like a million, well, not a million, like a ton of different reaction conditions, and none of them worked. the best one was when I got this. That was it. And
That was a good day.
it was good. It was good. It was a good day.
I don't have a question because I don't necessarily understand chemistry. But I do want to say congratulations to Kelly. This was such an amazing presentation. And I know me and the rest of our friends, like we watched you work on this project and how hard you worked and it came together and it's amazing. And I'm so proud of you. I was tearing up. So congratulations, and you deserve all the flowers for this presentation.
Thank you. Thank you, Megan.
Thank you, Megan.
Kelly, what advice do you have for the next poor soul who takes up the project where you left off? What warnings do you have for them?
That lucky soul. Oh, the lucky soul.
They're here. They're here in this room right now.
Yes, they are. Yes, yes. Well, what do I have to say? Oh, I can't wait for you to fail so hard. I can't wait for you to just do everything right and everything goes wrong. I can't wait for you to experience true research. I think that it took me this long to finally understand that 3 hours on the literature is the same as 6 months in the lab. That's another huge thing that I will give you. That's honestly the biggest piece of advice that I would have given anybody. All because if we had found that vinyl phosphonate maybe a little bit earlier, I could have maybe gotten the radical at this point. It doesn't seem impossible, but you have everything for it. And I really hope that you are successful. Do it, please. You got it. And let me know if you need any help.
Awesome. Excellent. Well, fantastic discussion. Still time for questions. We can hang out here. I'm going to stop the recording at that